is that using the kinetic theory of gases, Fourier's law for gases can be expressed as 1/3 CVL, where CV is the volumetric heat capacity at constant volume. So let's turn that into materials properties then, and then compare to what the experimental data shows. Okay, so that's 1/3 C. So C is, for a monatomic gas, that would be 3/2 times Kb times the number density. But instead of writing 3/2, a lot of molecules are actually diatomic. So for diatomic molecules, we would have found 5/2 instead of 3/2. So I'm just going to leave A as an arbitrary constant that is of order 1. Then the velocity, so the average velocity of a molecule, we could get from the Maxwell distribution for velocities. Involves square root of kBt over m was the key portion of that. And then the mean free path turned out to be 1 divided by the number density of molecules times the scattering cross-section. And what we find is basically that some of these terms cancel. So let's see. The most important ones here are basically that the number density cancels. So it turns out the number density of molecules actually doesn't matter at all. And so that's kind of unusual. That means that the thermal conductivity of gases actually doesn't depend on pressure. So if you start vacuuming gas out of a chamber, guess what? Unless you reach a super, super low vacuum such that, basically this is no longer the mean free path. At some point the molecules collide with the walls instead of themselves. But if they're colliding with themselves, it turns out that actually the thermal conductivity is completely independent of the vacuum pressure. Which is an interesting result. But the other thing, if you're sort of tracking which one of these things are actually properties of the gas versus just constants, it's basically like a whole bunch of constants times square root of T divided by the mass divided by the scattering cross-section. I guess it would be the scattering cross-section squared is the key thing, and then some constants sit up front. But the key thing here is that the thermal conductivity is proportional to the square root of temperature, and then it basically runs inversely proportional to some combination of the mass and the scattering cross-section. So keep in mind that the scattering cross-section gets smaller as the molecule gets smaller, right? So things with small mass tend to also have small scattering cross-section. So when you look at the experimental data I've shown below, I've plotted in 2 different ways. So I've plotted for some real gases, how does the thermal conductivity depend on the molecular weight? As you can see, very small molecular weight gases like helium. I haven't drawn hydrogen, but hydrogen's quite similar to helium actually. So very small gases tend to have very high thermal conductivity. Well, not very high, but much higher. So in the range of 0.2 watts per meter Kelvin, and very low thermal conductivity gases at room temperature would be less than 0.01 watts per meter Kelvin. So basically, what you see is this sort of downward trend of the thermal conductivity with mass. And on the flip side of that, the square root law for the thermal conductivity with temperature is almost exactly followed for all gases. And so basically it only stops being followed once you stop having an ideal gas. Once the molecules are jammed closely enough together to interact with one another, this wouldn't hold anymore. But basically the thermal conductivity goes as the square root of temperature all the way up until the point that the molecules dissociate. And so, it's a fairly good law. Now, I'll point out that some of the constants that sit in front here, when you're using kinetic theory of gases with the hard ball, or actually it's really not, this isn't really the problem, it's really this. So the way we've calculated the scattering cross-section, assuming that these are hard spheres previously, doesn't hold up super well. Like, I think you'll find that the predictions of this theory, if you actually plug in the numbers that we had for the scattering cross-section, are probably off by like a factor of 3 compared to the theoretical estimate of the thermal conductivity. And that's partially because we've assumed that like if the molecules touch each other, then they basically transfer all their energy. But in fact, like, not all collisions transfer all the energy, and a careful accounting of that would lead to a scattering cross-section that's more accurate and would include a better estimate that would be different by a factor of 3 for transferring energy. So there's a lot of I really don't go into a lot of detail here because it's really not worth it, but there is an entire book by a fellow named Hirschfelder that actually goes through the details. Let me see if I can find that. When was this published? That's a book written in like 1964 on the kinetic theory of gases. And it goes through a lot of the details of how you would do those more detailed calculations of the scattering cross-section more formally. I just don't think they're worth it. But you can actually get very precise results if you account for whether collisions are transferring the energy correctly or not. But anyway, but this theory is pretty good at helping you build an intuition for how the thermal conductivity depends on various properties. And I think we'll do a slightly better job of that when we do Boltzmann transport theory later in the course as well. We can build up the same kind of intuition for other sorts of properties, and that's what I'm going to do next. So I'll do viscosity and diffusivity next.